welcome you all in this presentation related with the subject materials processing fundamentals and practical. In this lecture, I will be talking about the importance of the plasticity of the metal and the metal forming. You know, metal forming is one of the very common material processing approach wherein the plastic deformation of the metal which is being processed is used to get the desired size and shape so that it can be processed further to obtain a product. To deform a metal by a plastic deformation, it is important that it has sufficient plasticity or ability to get deformed, which we commonly measure in terms of the ductility and the yield strength. The flow stress is one of the very common parameter which indicates how easily a material can be subjected to the plastic deformation. In this lecture, basically I will be talking about the importance of the plasticity in metal forming, basics of the plasticity in terms of the engineering versus true stress strain behavior, plastic deformation mechanisms by slip and twinning, the factors affecting the structure of metal and the plasticity, a role of the temperature and structure on plasticity, mathematical models related to the plasticity in metal forming. So, we know that the metal forming involves the plastic deformation of the metals, and for the plastic deformation we need to apply the forces using the external tools. Okay. So, to deform, you see, metal deformation needs application of the force. So, when the force applied develops the sufficient stresses to cause the flow of the metal, that too plastically, then it is subjected to the plastic deformation. Now, the force required to cause the plastic deformation depends on the temperature at which this kind of the force is being applied in a given metal. Of course, metal can be one of the parameter, but it is important to consider the temperature at which the force is being applied. So, the stress required to cause the flow of the metal plastically can be termed as a flow stress, and that flow stress is significantly affected by the temperature. Higher the flow stress, higher will be the force required. So, if we increase the temperature, the flow stress will be reduced, the force that will be required to cause the plastic deformation will be reduced, and therefore, the temperature forms a very big basis or the parameter to group the various metal deformation based processes. So, therefore, based on the temperature, we can have the metal forming like cold forming when the temperature of the metal being subjected to the plastic deformation is either at room temperature or it is less than the or it is close to the room temperature. Okay. Then hot forming when the temperature of the metal subjected to the plastic deformation is heated, temperature of the metal which is being subjected to the plastic deformation is heated above the recrystallization temperature. And if the plastic deformation of the metal is realized at the temperature in between the room temperature and the recrystallization temperature, then we call it as warm forming. So, cold forming, hot forming and warm forming in between. Okay. So, as far as the temperature is concerned, cold forming is carried out at a room temperature or close to the room temperature. Warm forming is carried out between the room temperature and a little higher than the room temperature or below the recrystallization temperature, and hot forming is carried out above the recrystallization temperature. So, with regard to the temperature, this is the sequence. Why it is important? Because the temperature directly affects the ease of deformation, and that we measure in terms of the yield strength, and the ability to get deformed, that we measure in terms of the percentage elongation. Okay. So, if we increase the temperature, yield strength of the metal comes down, and the ability to get deformed in terms of the percentage elongation that increases. So both these property variations go in favor of easy plastic deformation. What we can say indirectly, material's ability to get deformed is enhanced, and the stress required to cause the flow stress required to cause the plastic deformation at a high temperature is reduced, and therefore temperature becomes a very important parameter. So how to check all these things? The flow stress is one. Flow stress is the stress at which the material will start deforming plastically. So the flow stress corresponds to the yield strength if the metal is in the annealed condition. But if the metal is not in annealed condition, means it is having effect of some other metallurgical changes due to the plastic deformation or metallurgical transformation, then the flow stress will not be corresponding to the yield stress, but it will be different from the stress. Okay, and therefore it is important to use the ease of plastic deformation is evaluated or examined in terms of the flow stress. Okay, so the first parameter, how to check the yield stress of the material. If we talk of the engineering stress, then we have the stress in y axis and the strain in x axis. Then say for the common metals like mild steel, what it shows a typical stress strain curve, engineering stress strain curve like this. What it indicates, this upper yield point and the lower yield point. So this is the one zone where we see some kind of the deviation from the straight line, that is in the, this is the elastic zone. So in this zone, when the stress applied is up to the elastic limit, the stress strain curve follows the Hooke's law, and thereafter we will see some kind of the deviation at the yield point. This kind of the yield point is typically indicated in the BCC metals like iron or steels, and once the yield stress is crossed, the material starts deforming plastically. But at the same time, stress required to cause the plastic deformation in continue to increase with the increasing strain value. This is attributed to the work hardening, and thereafter reaching the multiple maximum stress level corresponding to the engineering stress strain curve, we get the ultimate point, ultimate strength point, and thereafter the stress starts decreasing. This is the point at which the necking starts in the material. So what happens initially when the stress is applied in a material, say tensile stress is applied, there will be increase in the length and a reduction in the diameter or cross section, which is uniform all along its length. Okay, increase in length, reduction in diameter is spread across the length. So this is the first stage, elastic limit. Okay, so then we'll see that on further increasing the stress level, there will be further increase in the length and reduction in diameter. Okay, this is also spread all along its length. So beyond the elastic limit, there will be yielding. If we continue to apply increasing stress level, then we will see that somewhere a localized reduction in cross section starts like this. Okay, so this localized reduction in cross section and a localized increase in the length starts. This is called necking. This happens at the level of the ultimate stress level, when the stress level applied crosses the ultimate strength of the metal, and then eventually the material will fail. Okay, then the suppression will occur. So when the suppression occurs, we will see it this point. This point corresponds to, if you just try to see it, this is the point 1 is initially stage 1, then stage 2 where it is the straight line relationship exists for 2, and then the yielding starts. Then here you will see the 3 when the yielding will continue, and then 4, this is corresponding to the 4. Okay, 2 and 3 and 3. Okay, and 4 and then 5 when the fracture will occur here. So, between 3 and 4 there will be the continuous increase in length, reduction in diameter throughout the length, okay, and this is the zone where work hardening will be happening. Okay, necking will start at the point 4, this is corresponding to the point 4, and at 5 there will be the fracture. So, the total change in the dimension in terms of the strain, this indicates the ductility. Okay, we measure in terms of the percentage elongation. Okay, so how far we are able to increase the length, how far we are able to deform the metal prior to the fracture, that indicates the ductility. Okay, stress and strain. Okay, so it is possible like one metal deforms like this, another metal deforms like this, and third metal deforms like this. So these are the different ways by which the deformation is happening. So here the elongation is this much, that is significant as compared to the other two metals. So if the metal is subjected to the limited deformation prior to the fracture, then that will indicate that it cannot be deformed plastically much, otherwise it will crack and it will fail. So to cause the plastic deformation for material processing, it is important that material shows lower yield point and greater elongation, then our ease of the deformation will be high. Okay, ease of deformation will be high. But here what is happening, when the engineering stress strain curve is plotted, what we assume that our the load being applied is divided by the original cross sectional area, and the strain is divided by the our original length. To obtain the strain, we use the original length. Okay, so instead of using the original length and original cross sectional area, if we consider the instantaneous cross sectional area and instantaneous length, then we will be getting the true stress strain curve. Okay, in engineering stress strain we got a curve like this. Okay, but if we use the instantaneous cross sectional area and instantaneous the length of the sample to calculate the stress and strain, then our curve will continue to show the positive trend. What it indicates that the stress to cause the deformation will continue to increase until the fracture takes place. So, this curve is the engineering stress strain and this corresponds to the true stress strain. Okay. Now, this kind of the behavior is shown. You see, engineering stress strain curve significantly depends on the type of the metals. Like say, so if this is strain and this is stress, say if we talk of the metals like steel, to trend like this. If we talk of the metal like aluminum, there is no deviation. Okay, there is no deviation like this, which will clearly indicate the yield point. In case of the aluminum, magnesium, these kind of the metals, there is no typical point at which the curve will deviate, but the curve is continuous. So in that case, we use the offset stress point, offset stress instead of the yield stress. So for metals like aluminum, magnesium, offset stress is used by drawing a line parallel to this initial elastic zone line, and line is plotted at the 0.002% strain. Okay, so the point where it cuts, that indicates the offset stress value. Okay, in yield, in case of the steels, we clearly get the value of the yield point from at the point where it starts deviating. So offset stress is particularly used in case of the certain metals which do not show the yield point clearly. Now, as far as the deformation is concerned, I have talked about the elastic and plastic deformation. Here what you can see, the strain and stress. So, initial zone where it is straight, this is the elastic zone, and then there is a little deviation and then it goes in like this. So, here the zone where it is straight, this zone follows the Hooke's law, and for this zone the stress is proportional to the strain. If you want to determine the what will the stress required for given amount of the strain, then we can simply multiply the strain with the modulus of elasticity get the stress, because there are direct stress and that proportionality, okay, between the stress and strain within the elastic limit. And if the applied stress is greater than the elastic limit, then material will start yielding and will a permanent deformation will set in. This is the zone of the plastic deformation, and this is a zone where the material will be subjected to the work hardening. Okay. So, the stress for plastic deformation, as I have said, the material in yield condition. So, the yield point directly indicates the stress required to cause the plastic deformation, but if the material is in other than the annealed condition, then we use the term flow stress. Okay. The stress at which the material sets in the plastic deformation, that can be significantly different from the yield stress of the material. Okay. We have already talked about the engineering stress strain diagram, the stress strain diagram wherein the stress and strain are calculated based on the initial dimensions of the sample. The yield stress of the BCC and FCC metal is different, is obtained differently. Yield stress for, as I have said, yield stress for BCC metals is obtained from the yield point directly, but offset stress is used for determining the yield stress of the BCC metal. So, what we use offset stress. Okay. And as I have said, flow stress and the yield stress, these are different. Yield stress is correspond to the stress required to cause the plastic flow of the material in annealed condition, and the flow stress is the stress required to cause the plastic flow of any metal, including the metal in annealed condition. So, flow stress can be the yield stress or any other value. If the material is in any other condition, like in work hardened condition or metallurgically transformed condition or any other condition that is leading to the different the stress required to cause the plastic deformation than the yield stress, then to clarify that, to have the clear value of the stress at which the plastic deformation will be taking place, we use the yield stress. Okay. The flow stress and work hardening, these are directly related. So, when we work harden and cause the plastic deformation, like say this is the material in annealed condition offering us the value of the flow stress sigma 1. Okay. And so, this will be corresponding to the sigma y because material is in annealed condition. Okay. If this is subjected to the plastic deformation, then the stress required to cause the plastic deformation will not be corresponding to the yield point, but it will show the it will be using the flow stress, and flow stress is the flow stress required to cause the plastic deformation of the material in work hardened condition. Then it will be the significantly greater than sigma 1 or sigma y, which was in annealed condition. Then our sigma 2 will be greater than the sigma 1 or sigma y. Okay. So, the flow stress required to cause the plastic deformation of material in a already plastically deformed condition, that will be needing the higher level of the stress. So, here this is the sigma 2. Now, when a material is subjected to the plastic deformation, as I have said, it experiences the work hardening, it experiences the decrease in ductility, it experiences the increase in the yield strength, and also it increases the ductile to brittle transition behavior. So, the few changes are experienced when a material is subjected to the plastic deformation. Increased yield strength means increased flow stress required, then increase in ductile to brittle transition temperature, the temperature at which material loses its the toughness, that increases actually with the plastic deformation. Then material's hardness is increased, then there is a decrease in the percentage elongation, means material's ability to get, material gets hardened and its ability to get elongated, that is decreased. The effect of temperature and work done on plastic deformation. So, we know that when the temperature is increased, materials yield strength is reduced, flow stresses are reduced, and that in turn decreases the work required to cause the plastic deformation. We will be seeing these things in detail. So, the plastic deformation and the yield criteria. Stress required to cause the elastic deformation, specific elastic strain can directly be obtained by using the true stress strain diagram simply by drawing a vertical line from the point of the desired elastic strain. It is like this. So, if this is the elastic strain, we can draw a vertical line and multiply this strain with the modulus of elasticity to get the stress required. Okay. So, in case of the true stress, this curve will continue to go like this. Okay. Now, the intersection of the vertical line with the stress strain curve gives the amount of stress required to give the to cause the given elastic strain. Stress strain diagram of metal like carbon steel, alloy steel clearly shows the yield point indicating the minimum stress required to the commencement of the plastic deformation in a given metal condition. So, this is about this, like metals like steel will show the deformation engineering stress strain curve like this, and this yield point where it shows some kind of the deviation that indicates the minimum stress required to cause the commencement of the plastic deformation in a given metal condition. For FCC metals and flow stress, however, many FCC metals like aluminum, copper, austenitic stainless steels do not show any specific yield point, and in those cases we use the offset yield point. Okay, stress. So, as I have said, if the material is showing curve like this, then at the point 0.002% of the strain, a line is plotted parallel to the elastic limit point, and wherever it cuts, that is used as the offset yield point stress, and this is particularly used for aluminum, copper, magnesium and other FCC metals. Stress corresponding to the yield point is the flow stress to be applied to realize the plastic deformation in a metal without any work hardening effect. Okay. So, this is what is done especially when the yield point indicates the flow stress in the annealed condition, but not in the when it is not having any kind of the work hardening effect. It is important to note that given amount of the plastic deformation in terms of the plastic strain can be obtained by multiplying the specified value of the externally applied stress. The flow stress and work hardening. However, the commencement of the plastic deformation strengthens the metal due to the work hardening and thereby increases the stress required to cause the further plastic deformation. That is applicable for this zone. This is the zone where plastic deformation sets in. So, to cause the further plastic deformation, it requires higher and higher level of the stresses when the plastic deformation sets in, and this is attributed to the work hardening in engineering stress strain diagram. Okay. Therefore, it becomes essential to consider the work hardening behavior of the metal in the plastic deformation based manufacturing process. To therefore, for determining the force or stress required to for manufacturing. So, how much stress or force should be applied to cause the plastic deformation so that the material can be given desired size and shape. It is important to determine that how to get that value of the stress required. So, we need to determine the flow stress of the material when it is subjected to the plastic deformation. So, flow stress is needed to realize the given plastic strain of the metal having the work hardening exponent, and then the flow stress can be obtained using the following relationship. Okay, sigma is equal to the x epsilon raised to the power n. N is the work hardening exponent, x is the material related coefficient accounting for strength, and it is also denoted as a k, and this is the strain, the epsilon is showing the strain that we want to induce. Okay. Then the work hardening behavior of the material is observed during the plastic deformation of the metal below the recrystallization temperature. So, the increasing stress requirement with the plastic deformation, this is true especially when the deformation is done under the room temperature condition. Okay. If the deformation is carried out at a high temperature, then material does not show the work hardening behavior. So, the flow stress to cause the given amount of the plastic deformation can be obtained by this equation. But see, we have seen that stress required to cause the plastic deformation keeps on increasing with the plastic deformation. Then we need, so the flow stress in the beginning is less and flow stress at the end is high. So, it is important to get the average value of the flow stress. Okay. So, since the work hardening and the stress requirement continuously increase during the plastic deformation, therefore, flow stress used in manufacturing to realize the given plastic strain is considered as average flow stress. The flow stress continuously increases from the commencement of the plastic deformation beyond the yield point till a specified plastic strain is achieved. So, this is the target, but since the stress requirement continuously increases, therefore, it is important to go for determining the average flow stress. And average flow stress is determined like say using this equation. Average flow stress needed to realize the given plastic strain of the metal having the work hardening exponent n is obtained using this sigma average is obtained from the x epsilon n divided by 1 plus n. Okay, n is the work hardening exponent, epsilon is the desired strain to be achieved, n is the work hardening exponent, x is the material related constant. Okay, if the deformation is carried out at a higher temperature, then we need to see that the stress required will be reduced. So, under the hot working conditions, yield strength is reduced due to the recovery and recrystallization, and the work hardening effect is almost absent. Okay. Therefore, plastic deformation of metal under hot working condition is easier and requires less power and force to cause the plastic deformation. Effect of temperature, strain rate and recrystallization on flow stress can be expressed using the following equations. Say this is the stress to cause the plastic deformation under given set of the conditions of a stress, strain rate and the temperature. Okay. So, here this is the equation you can see wherein x is the material related constant accounting for a strength, epsilon is the true strain, n is the material or strain hardening coefficient and epsilon italic in strain hardening rate, m is the strain rate sensitivity exponent, b is the material constant and t is the temperature. So, what it shows that these are the various factors like true strain, the strain rate, strain rate sensitivity, material constants and the temperature. These are the factors need to be accounted to determine the flow stress at a given temperature. Okay, work to be done during the plastic deformation will certainly be the function of the work done in deformation per unit volume is obtained from the stress into the strain. Stress is stress multiplied by area will give us force and strain multiplied by original length. So, this will be equivalent to the force into the deformation and that can be obtained using this the average stress and the strain that is to be realized, that will give us the work needed to be done for deformation per unit volume of the material. Now, I will summarize this presentation. In this presentation basically I have talked about the fundamentals related to the plastic deformation and what are the characteristics of materials should have so that it can easily be deformed. Thank you for your attention.